topic of today's lecture are Bode plots. And Bode plots are really important if you want to analyze your circuit and know how your circuit behaves at a certain frequency. So if we remember, our network function h is equal to the magnitude multiplied by some kind of phase. So in the Bode plot universe, we will express our network function using Euler's number to simplify our derivations. Gain of the network function will be expressed as 20 logarithm to the base of 10 h in decibels. Please remember that this is always the case. So, for example, if we take, let's say, the formula of a low-pass filter, the gain, the magnitude, is 1 over 1 plus omega over omega 0. And our phase is tangent, let's say arctangent, omega over omega 0. Bode plot usually has both magnitude and phase plots, but in this lecture set, I'll only focus on magnitude plots. So the gain in this case can be expressed as minus 20 logarithm to the base of 10, 1 plus omega over omega 0 squared. Please remember that this is true. So if we want to analyze how our circuit behaves, let's say at some frequency, we call it a corner frequency. So this will be, let's say, a corner frequency. So the magnitude can either go up, it can go down, or remain steady. So this corner frequency, we want to see what happens to our circuit, and we apply two assumptions. The first one is a low frequency assumption. In this case, we assume that our omega 0 is so large that their ratio becomes almost negligible, and we equate it to 1. In that case, our gain is 0 decibels. The second assumption is when our omega is much larger than omega 0. In that case, this term over here becomes comparatively very large, so that we can neglect 1 and equate it to simply v over omega over omega 0 square. In that case, our gain will be equal to 20 multiplied by logarithm to the base of 10 omega 0 minus 20 multiplied by logarithm to the base of 10 omega. If I were to draw the Bode plot of this low-pass filter, it would look somewhat like this. So it's important that in the x-axis, we usually have values that are 10 to the power of some number, let's say 1, 10, 100, 1000, and etc. So it's always 10 to the power of 0, 10 to the power of 1, 10 to the power of 2. And on the y-axis, we usually have 0, 1, 20, and it's not always the case. So this is our gain, and gain is not always 10, 20, and all of these pretty numbers. Gain can be very ugly. It can be 6.19, it can be 6.49, and whatever. But please remember that in the x-axis, we always have 10 to the power of 0, 1, 2, and etc. So usually what we have is some kind of exact representation. So let's say this is an exact curve. But when we draw Bode plots, they usually look like this. They look very sharp, and we call it an asymptotic plot or asymptotic curve. This is exactly what we call a corner frequency. So the corner frequency is a place where both high and low frequency assumptions occur. Let's solve an example. In this case, we have to draw the Bode plot of the following circuit. And honestly, for us, it's enough to know how the network function behaves at low frequency and high frequency assumptions. It is not necessary for us to know the value of the constant k of omega 1 and omega 2, because for us to draw the general Bode plot for this particular function, it's enough to know the expression. So we will start with our assumptions. And since we have 3 values of omega, we therefore have 3 assumptions. So our network function will be equal to something something at omega less than omega 1, omega greater than omega 1 but still less than omega 2, and omega greater than both of them. Okay. So here, in this case, in case 1, omega is less than both omega 2 and omega 1. In that case, these 2 terms become so negligible that the whole thing will become k multiplied by 1 plus 0 squared, and the same goes in the denominator. So this will simplify to just k. In the second case, when our omega is already greater than omega 1, we will still consider that this term is negligible, but this term over here is no more negligible. And in that case, the effect of 1 is indeed negligible. So what we will have is k multiplied by omega over omega 1 squared over 1 plus 0 squared. In that case, we simply have k multiplied by omega over omega 1. So in the third case, we will have both of the terms non-negligible. So this will no longer be 0 and this will no longer be 0. In fact, they will both contribute, and our k will be multiplied by omega over omega 1 over omega 2. And in that case, our network function is nothing else but k multiplied by omega 2 over omega 1. So now that we see how our circuit behaves at certain frequency changes, we can draw the Bode plot. So we will only draw the magnitude plot of the Bode plot, and it's essential for us to know some important points, important features of the Bode plot. So first of all, in the x-axis, we have values to the power 10 to the power of something. So it's usually 10 to the power of minus 1, 10 to the power of 0, 10 to the power of anything essentially. So when you will have some certain numbers instead of just pure coefficients like k, you will have, for example, 2 instead of omega 1, you will have 10. You will plot it on an axis that has, let's say, 0.1, 1, 10, 100. It is not the usual 1, 2, 3, 4. It is now the Bode plot universe, so forget about that one. In the y-axis, we have the gain, and gain usually doesn't follow a strict rule. You may have gain equal to 10 minus 6.2, and it doesn't matter. But we usually plot everything in the upper, let's say, upper area. So this is our 0, this is our minus 10, this is minus 20, this is 10, and this is plus 20. So in that case, in our specific example, we don't have any values, so I will just assign some arbitrary points. Let's say omega 1 and omega 2, it does not matter. In that case, omega 2 is of course greater than omega 1. And as we may see, before omega was greater than omega 1, it's less than both omega 1 and omega 2. And what we see from our approximations is that in this particular case, our network function is equal to k. And if we want to know the gain of our network function, we take 20 multiplied by logarithm to the base of 10 of h. In case 1, it will be simply 20 logarithm to the base of 10 of k. And this is nothing else but a constant. So we express a constant as a straight line. So for a moment, let's forget about these values because they'll kind of confuse us. And we'll draw a straight line up to the point where we reach omega 1. So this is the point where something might change, and it does indeed change. So as we remember, our term, our omega in the numerator is a 0, and a 0 always leads to an increase in the Bode plots by 20 dB if it is omega to the power of 1. So it means that there is only one frequency at this particular point. If you have, let's say, an expression that is 1 plus GV over omega 1, then it will increase by only 20 dB. But if you have two zeros at one frequency, it will increase by 40. It will be plus 40 dB. If you have 3 of them, it will increase by 60 dB, and so on. But for now, since we have only one point, only one zero, that is at omega 1, it will increase only by 20 decibels, plus 20 decibels. As easy as it is. So here is another important point. So here we observe what happens to our function. As we see, this is nothing else but a pole, and there is only one pole at this particular frequency. It follows the same logic, but in the opposite sign. So whenever we have one pole, it leads to minus 20 dB. Something like this. If we have two poles, so omega 2 to the power of 2, it will decrease by minus 40 dB. So it will be sharper, and so on. So here, since we already have a plus with a slope of plus, let's say a slope of plus 20 dB, we subtract now 20 dB from it, because here we have a pole and it will again become a straight line. So this is our Bode plot for this particular circuit, and I hope you find it helpful.